So now what we want to do is actually try and exploit this. In our last run we just gave it 4 A's as the input, and they showed up in memory, and they seem to be, well, backwards. And here's our return address right here. If we recall, that is the next instruction in main to be executed, so we want to overwrite that return address. So in this case, we could really just count how many bytes we need. As we'll see with later exercises, that's not always going to be the case. But we put in 4 A's before, so here's 5 with the null, 6, 7, 8, 9. So it looks like we need 9 bytes of padding, and then naturally 4 bytes to overwrite the return address. Hex 2 digits is a byte, so we want 9 bytes of padding and then 4 bytes to overwrite the return address. Again, in this case, we can just count. So let's run this again. Again, that's run, and then we can put in 9 A's and some B's, but eventually we're going to have to use scripting anyways. When we start using a return address, it's made of hex instead of just some B's. So let's go ahead and do that. So if we do a $sign and then open parentheses, we can run a script here. So we could do Python or Perl or any scripting language that this Ubuntu system knows. So we're going to use Python for the rest of our exercises, so why don't we use Python here. So let's do Python-C to tell it to run a command. Open single quotes, and I want to print double quotes A times 9 plus double quotes around B times 4, so that's A. So our 41s times 9 for our padding, and then B, which will be the next number in hex, which is 42. Again, you can look at an ASCII chart for that if you are not familiar with these. And so 4B's is going to be overwriting our return address here. So this should make the program crash, so we want to close up our command. So we need a single quote here at the end, and then close parentheses. So this is going to tell it execute this script, and whatever the output is going to be our argument. So in this case we could have just typed out the A's, but again, when we want to turn this into an actual hexadecimal address, really the only way to do it is using scripting. If we just like type in 08048443, it will take that as 8 different 1-byte characters instead of hexadecimal. So let's go ahead and run this. Our breakpoints are still going to be set. We can delete them, or if we restart GDB they'll go away, but otherwise they will stay, and we want them for now, so just leave them. Let's go ahead and run it. Alright, so we hit our first breakpoint. Again, that is in main, so before we call function. So again, we can examine an x slash, let's see, I believe it was 12 bytes. Well, let's just leave it and say 16 again. We'll just do too many. So 16 hexadecimal words from ESP. Again, that is the top of main stack frame. Notice that we have moved up the stack some, so our last digits are 20 here. Whereas previously in main, I believe we were at C0. If this is the return address, then this is the top of main. So we have moved up the stack some. That is to be expected. One of the things that makes a difference about where you end up in the stack is going to be the length of the argument. So since we did change the length of the argument, we should expect to move somewhat. Shouldn't change our next round since we've got our 13 character input, so we should expect to be in the same place next time. But that's nothing to worry about. What we really care about is our offsets, just to make sure that our 9 A's plus 4 B's will overwrite that return address. So as long as our stack frames are the same length and our data is going in the same place inside the stack frame, our addresses don't particularly matter. Okay, so let's examine, just to make sure that our stack frame is the same size. Let's just examine one hexadecimal word from EBP, our bottom. Sure enough, this is still main stack frame, so still rather short, 12 bytes. Alright, so let's go ahead and continue. Move us into function where we hit our second breakpoint. We'll use the up arrow to grab previous commands. So I will again look at ESP. And now we have moved up some more. Notice what hasn't changed here is we still have the return address 08048443. We can again do a disassemble main to see that. So here is our call to function. When that returns the next address to be executed, 08048443. So that should be our return address. If we examine from EBP again, remember ESP and EBP are now inside of function stack frame. So sure enough, same size stack frame here, return address, and then main here. Alright, so let's continue and hit the string copy, let that execute. We hit our third breakpoint right after the string copy. Now if we take a look at our stack, we have our 41 over here by itself again, all 41s here, those are our big A's. Big A's here, and then where the return address was, we indeed have 42, 42, 42, 42 for uppercase B's. So our offsets are correct, and we have managed to overwrite that return address. So what's going to happen now is that the program will just continue on as it blindly does. So we'll get rid of the stack frame here, we'll be wound off the stack, and it will just automatically try and load this address. So it will load that address into EIP. We can always do info registers. I didn't mention that, but we can do info registers here and see all of our registers. So again, our 42, 42, 42, 42 will be loaded into EIP. Whatever is at that address, if anything, will be executed next after function returns. If 42, 42, 42, 42 is not that mapped to an executable portion of memory, then we will get a segmentation fault and it will crash. That is most likely what's going to happen here, though there's no rule that says 42, 42, 42, 42 cannot be a valid memory address. You may find cases where it will be. So we shouldn't just blindly assume the program is going to crash, but often it will. So let's go ahead and continue. And this time we do not get executed normally printed out to the screen. We get a segmentation fault. So it's trying to execute 42, 42, 42, 42, and that's not mapped to anywhere, so there's no instruction there to be executed, so the program just throws up its hands and crashes. So we've caused a denial of service condition, but surely we can do better, right? So let's see indeed if we can.